All right, let's try a few more examples. I know I keep saying this, but it really just, it comes down to practice. So we're just trying a few more examples here. And this time, we're going to be using chain rule, but we have some inverse trig functions to contend with. So how's it going to work? And the first thing we're going to do is just say a little bit about the kind of the notation here. So the notation can get a little confusing with inverse trig functions. And that's because this -1 is not actually an exponent. So let's look at the first one here. This 1 over inverse sine of x. We want to differentiate this thing. And how we're going to do it is we have a fraction here. So the way we generally contend with fractions, we might think quotient rule, but if we look at this, there's no variable term on the top. So if there's not a variable on the top, we don't necessarily need to use quotient rule. And generally the way we handle fractions in that case is to rewrite them with a negative exponent. So that's what we're going to do. We're going to rewrite this with a negative exponent. So I'd write this as sine, inverse sine of x, all raised to the -1 power. And, ooh, that looks confusing. And it does. And it's kind of one of the things, the inverse notation can look a little confusing. And why? Well, this -1 is an exponent. This -1 is not an exponent. And they look identical. So when we have these inverse trig functions, when you read this, almost read the -1 there as just being part of the name of the function. So think of this as just, that's the name of this function, inverse sine. Here's the name of that function, inverse cosine. And then here's the name of inverse tangent. So the -1 here, even though it kind of looks like it's an exponent, it's not an exponent. It's just part of the name of this function. So it's the inverse sine function. It's inverse sine of x, all raised to the -1 power. So that's sometimes why I like arc sine of x and arc cosine of x and arc tan of x. They kind of avoid that ambiguity. A little bit wordier here, but they kind of avoid that ambiguity. And it's even more confusing because we saw in a previous example, we saw something like secant cubed of x. So this cubed here is an exponent. It's secant of x all cubed. So, you know, the notation here can get a little tricky. So if you see a number here right next to the trig name, generally it is an exponent. But when it's a -1, if like sine of -1, it's actually not an exponent here. This is just telling us we have the inverse sine function that we're dealing with. So just keep that in mind for these inverse trig functions. The notation can get a little tricky. All right, so how are we going to differentiate this thing though? Well, when looking at this, we have this inner function, inverse sine of x, but then our outer function here is just a power function. So we would differentiate this just like usual with the general power rule. So how does the general power rule work? Well, we take this exponent, bring it down, put it in front. So I'll put the -1 in front. Keep the inner function the same. So inverse sine of x is going to stay the same. And then I'm going to subtract 1 from our old exponent. So that's going to take me down to -2. And then I take the inner function, which is, again, inverse sine of x, and I multiply by its derivative. All right, so now I need to remember, what's the derivative of inverse sine? Well, here we go. Derivative of inverse sine is this 1 over square root function. So it's 1 over the square root of 1 minus x squared. And there we go. We have our derivative. So maybe the notation kind of gets in the way a little bit on this one, but we made it through. And there's ways you can clean this up. So you can turn this back into a fraction. So it could be 1 over inverse sine squared. But this is perfectly good. All right. Let's try another one. Here we're using the arctan notation. So we have y equal to arctan of 3 of x, or 3x. We want to differentiate this thing. What's the outer function? What's the inner function? So I see a nice set of parentheses here. What's inside those parentheses is going to be my inner function, so 3x. And then arctan is outside, so arctan is going to be my outer function. All right, so my outer function is arctan, or inverse tan, and my inner function is 3 of x. All right, so pretty good. Let's differentiate. So what's the derivative of arctan? Well, it's 1 over 1 plus x squared. So whatever your inner piece is, it's 1 over 1 plus that squared. So if I'm looking at this, my inner function is 3x. So when I calculate the derivative, it's going to be 1 over 1 plus whatever I had there squared. So my outer function is arctan, and the way you differentiate it, it's 1 over 1 plus your whatever term you have inside squared. So in our case, differentiating arctan, we're going to have 1 over 1 plus, we had a 3x inside, so the 3x is we're going to keep it the same. It's going to be a 3x squared here. So this is the derivative of our outer function with that inner function plugged in. Then we take that inner function and we multiply by its derivative. So derivative of 3x. And derivative of 3x is just 3. And it's usually good to take that lone 3 and just put it into the numerator here. So we get 3 over 1 plus, and I guess we could simplify. So distribute the squared, we get 9x squared. If we wanted to simplify a little bit. All right. Well, we're going to do, I know I say this each time, we're going to do a few more examples. So really this chain rule, this is one of our more complicated derivative rules. And it just comes down to practicing these. But what we're going to see in the next example is, so far in all the ones we've done, we've only had to use the chain rule once. So you can always see when you've used the chain rule because you're always multiplying by this term, the derivative of a term. And so once in the next example, we'll see why it gets the name chain rule. So we'll see you there.